Right, in this class we will try to look at unsupervised learning and clustering. As we observed before, in unsupervised learning you have some points x1 up to xp or data points, and you either try to visualize the samples or discover something about them. Right? In supervised learning you wanted to predict some y, usually y was part of the observation. In unsupervised learning there is nothing like that, so we'll see how that goes. Right? We had for visualization PCA and TSNE, and today we will try to discover something about clusters, in our case clustering. Okay? Bunch of methods for it, so we'll look at two of them. We'll do k-means clustering, where we try to find good points for centers of clusters by moving them around, and hierarchical clustering, where we try to group together clusters that seem to be close to each other, or points that should be close to each other. Clustering, we'll again use the iris dataset because we have a good guess how the clusters should look like. So first we'll prepare the dataset a little bit. Use standard scaler and PCA for displaying it in 2D. So you load the dataset, and I do the standard scaler, and I also do PCA for drawing it. Use scatter plot. I use the coordinates after PCA, and this is the projection in first two coordinates. This is a two-dimensional visualization of the iris dataset. Here is the mathematical formulation of k-means clustering. I have data, I have p points, and I have k clusters. The k is fixed, I fixed it in advance. And for each of these clusters, I pick a center. The centers, 1 up to k, do not have to be the data points from the original data set. They can be floating somewhere with whatever coordinates they have. Right? And then what I would like to do is partition the data points x1 up to xp into k different sets, k disjoint sets, and for each of them I will call them clusters. I will calculate how far these sets are from the centers. So let's say the mu I is the center for cluster I, and I will go over all data points that I assign to the cluster I, and I will calculate the difference of the point from center of the cluster it belongs to. Right? So I'll calculate, there is the difference norm square, so we are calculating the distance. How far is the point from the center of the cluster it belongs to? And here says we want to optimize it. By optimizing, we want to minimize this quantity. The trouble with this algorithm, this problem, is that it is NP-hard. NP-hard means that there is no polynomial time algorithm known that would be able to solve it quickly, and there are many other hard problems that can be solved if you could solve this quickly. Okay. So we are not going to solve it exactly, but we are going to approximate it. Right, so how does the algorithm work? You know how many centers you need to start with, so you throw in the random centers. Right? You can follow on the pictures on the right. Everything is in, you have a bunch of data. Then you throw in 2 points. By x, we assign them as the centers. Right? The blue x and red x. And then for each point, I calculate if it is closer to the red center or to the blue center, and that's how I create the initial partition. All right. And now I will look at the red points and say, well, it would be good if the center of the red cluster was in the center of the red points. So I calculate the center of the red points. And for the blue cluster, I do the same. I calculate the center of the blue points. And then the points, then the centers x red one and blue one move to the centers of the points. Right? And now I have new location for the centers, and I recalculate where each point belongs. And if I recalculate where each point belongs, I can try to recalculate where the centers should be. So it's a algorithm that alternates between the locations of the center and what points are assigned to each cluster. It's and when do you stop? There are two options. Maybe you stop when there is no change between what points belong to which cluster, or you can stop if you observe that the centers of the points somewhat converge slowly to certain positions. Okay? It's not guaranteed that things like that will happen, but this will be a reasonable output usually. A question is how good a clustering is. Okay? So if you get two different clusterings, how similar are they? Right? Would like to know how similar are two clusterings. You want to do it if you have something like clustering that you know is the correct one, and you want to test how your clustering is doing. Or if you have two clusterings, you want to see how similar they are. Right? So we'll do a little bit of math for this. Let's say n is the number of points, right? And a is the number of pairs of points that are in same clusters, and b is the number of points, pairs of points that are in different clusters. Right? So I look at here is the clustering P1 and P2, and I look at every pair of points. And if let's say the points N1 and N2 are in the same cluster in both P cluster in B, P1 and P2, then I get +1 to A. And if they were different clusters, then I will not get +1 to A. For example, if I look at N6 and N8 in P1, they are in the same cluster, but in P2, N6 and N8 are in different clusters, so I will not add +1 to A. So A is saying how many pairs of points are in the same clusters in both clustering P1 and P2. Right. And then I also count how many points are in different clusters. So if you look at N1 and N3, they are in different clusters in P1, and N1 and N3 is also in different clusters in P2. Okay, so both clustering P1 and P2 say that N1 and N3 should be in different clusters. So then this will do +1 to B. Right. And now we look and see how many pairs both of the clusterings agree on. Right? It's the A plus B number of pairs where both clusterings agree that should be at the same cluster, plus the number of pairs of points where both clusterings agree they should be in different cluster, divided by the number of pairs. So n choose 2, which is n times n minus 1 over 2. Okay? And if the clusterings are the same, then you get r equals 1. You can look at the calculation of R on the right, where you look at the 3 clusters. You get in the first one you get 1 pair, in the second one you get 1 pair, in the third one you get 3 pairs that are the same, and then for the B you get those that are different for every pair of the clusters, and calculate R. The little trouble with this is that if you have a large number of clusters, then many clusterings will agree on different points being in different clusters. So B will be very high, and it will be hard to tell. Right? So this is a little downside sometimes. You should be mindful. One would expect that if you pick 2 random clusterings, then maybe R should be 0, but it's not the case. If you have lot of clusters and you pick 2 random clusterings, the R may be fairly large. K means clustering. So okay, I will create the class K means. I will say how many clusters I want, and 3, and in it just automatic. I guess this was the default, you don't need it. And now I have the did I mess up? And clusters. Right. Now I will try to fit the clusters. I put the data in there. Right. Now I have fitted the data, and I can look what are the labels. It tells me for each entry if it is in cluster 0, 1 or 2. Right, very good. And I can try to draw it. So I'll copy the drawing that we had before, and here I will do the KM labels as U. Right. Now this is the clustering, where this is one cluster, another cluster, and third cluster. It's it doesn't perfectly distinguish which type is which, but this tube now has 3 blobs. Right. I have 3 clusters, and I would like to know what are the centers of these clusters. So, you can get the centers. So the centers are you do the km dot mistake. Cluster centers. Good. I pressed tab. So here are the points for the cluster centers. Right. I have 3 points. Each of them has 4 dimensions. Remember, we are working in 4D space. This is just a projection to a 2D space. All right. So I will try to draw them, plot, scatter, and I will, let me do it like this. Centers, this, so I'll centers 1, to 2 coordinates, label centers, and make it easier to see. See if it works. Right, I drew the centers like here, here, and here. They don't look like being in the centers of the clusters. Right? So, problem is that we are working in the X-scaled version, but we are drawing the things after PCA transformation. So I need to do the PCA transformation on this as well. Here what's happening is I don't do fitting on the clusters, I do just the transformation, so it's used the same transformation as the X-scaled was using, right? And now the centers of the clusters are somehow in the centers of the clusters, right? Good. Maybe I should also do the legend, and now it edited it. You see these are the centers. Right. We can try to see how accurate it is. Right? So, thing that I could try to do is print accuracy score km dot labels and y, and it says 0.28. I don't know, it seems to me that more than 28% was classified correctly, right? What the problem is if I look at y, I'll do print y and print AM labels, is that the class that was here first in the y is called 1, and the class that was here mostly 1 is called 2, and the class that's called 2 is called 0. So it changed the permuted the names of the classes, right? And then now the score is 5%. Now it's 52%. Right? That's, I guess. Well, now I have two clusters that are over here, and this is mostly correct. Now it's 13%, but it should not be. It should be much higher. The problem is that the one would have to permute the labels and try to take the highest accuracy score. Okay? So what you can try to do, metrics, use the rand score, and maybe life will be better. Because now 1 is best, so 81 it's pretty high. Right? So again, here maybe kind of higher number for the accuracy score, because now we managed to get the first cluster at 0, the second cluster is mostly 1s, and the last cluster is mostly 2s. So now when we were lucky and the labels we got from the clustering algorithm from the k-means are in the same permutation as for the y, we have high accuracy score. And this is the rand score, which is also fairly high. K-means clustering is also a classifier in a way, right? Because it identified the different clusters or the different species, kind of if you have the same number of categories as the number of clusters. So here it is written as classifier. You can use the cross validation on it, and you can do it with x scaled or original x number of folds, and then you have to say what the scoring function is. And the accuracy score would not be great, but the rand score is okay. And here is some experiment how well it does if you have different folds. Right? Looks like actually the not scaled version is doing better than the scaled version. So from the 5 attempts, and then here is the mean. Right, so this was just a little bonus for you. Another type of clustering is hierarchical clustering. In this case, you start with either each point being its own cluster, and you try to merge nearby clusters. It's called bottom up. Or you do the opposite. You start that everybody is in one big cluster, and you try to divide the cluster into smalls. So keep dividing until eventually you have clusters of size 1. Okay? In the bottom up, you keep merging until everything is in one cluster. Right? And somewhere in between, hopefully, there is some case that you have k clusters and they look reasonable as clusters. So here is or the bottom up. What do you mean by merge nearby clusters? That's maybe a good question. Nearby clusters, you can measure distance between clusters. How do you do it? A few different ways. I guess better to see it with pictures. You can say that two clusters are as close as their two nearest neighbors. That is one way to. Another way is saying that you look at the data points in each cluster and take the maximum of the pairwise distances, and that is the distance. Or you look at the centers of the clusters and make the distance of the center of the cluster the distance between clusters. Or you look at every pair of data points from each cluster between the clusters and take the average distance of these. And each of them may be good for different application, and each of them may give you slightly different clustering. Agglomerative clustering. We will first have here the data as usual. I will try to find maybe 3 clusters in here. So I'll create the object that does the clustering. Clustering model. Okay, it's agglomerative clustering, and I will say how many clusters I want, and then I will fit this X scaled to it, right? And then I will change the view here. View, let's comment out this clustering model labels. Right, let's see. Right, and now I have 3 clusters. What you can try to change is how do you define distance between the clusters. There's a linkage, and I wrote various linkage, different distances you can put in. Maybe this one didn't look great. Average complete. Yeah, create some other types of clusters. Maximum. Maybe it doesn't work any single. Right, looked like the part which was the minimizes the variance of clusters being merged. This maybe look the best for our purposes. But you should experiment with different linkages if you have your data, and maybe some of them will create nicer looking clusters than others. If you do a clustering in either way, such that you end up with one cluster at the top and many clusters at the bottom, you can somehow remember the history of how the clusters were merging or dividing, and you create this dendrogram, a representation of clustering. On the right you have it as a tree where you see always 2 clusters that you are merging as you go up, right? Or you can see it as clusters that splitting up as you go down. Here it's also drawn is nice 2D representation, doesn't always have to have nice 2D representation. Program, and you can call method linkage that will create all the links. Try to merge all the clusters. You can type which method you want, and then there is a function that will plot it for you. If you run it, it will show you. You cannot really see which species is which, but you can kind of tell these are the same ones, and it shows how are the things merged together, which clusters are merged at which point, right? So you can have some idea if the species are merged together early correctly or if not. So it's a fairly complicated picture, very few comments. What is a good question is, if you have clusters, how do you pick the right number of clusters? Right? So you can look at the dendrogram. It will tell you maybe when things become close, or you can experiment with different k for the k-means clustering, and you can also look at the clustering. You create some, and then you try to look at the data after PCA or t-SNE and see if you have a similar or if the clusters close together. This is not a precise science anymore. It's more like, does it look reasonable? It is open to interpretation. If you want to see more technical things about clustering, StatQuest, great resource.